I'm Nicolai Parlog. I'm a Java developer advocate for Oracle. And today it's going to be you, me, and data-oriented programming in Java 21. And we're going to look a little bit into 22 as well. As Brian Getz once said, I prepared too much, so I'm going to talk too fast. If you have any questions, don't wait for me to take a breather. It's not going to happen. Just raise your hands or just talk straight away. Otherwise, I'll be here for the rest of the day and after the talk as well, of course, so you can ask questions at any time. So we're going to talk about data-oriented programming. I'm first going to give you something that is not really a definition, but gets close to it, but it is also borderline useless. So what we're going to spend most of the time on is a lengthy example, where we go through and applying these guidelines, and we'll see where that gets us. And if you have time at the end, we're going to do a little review of what we just explored. If you want to see the slides, they're already online. It's slides.nipafx.dev. You will see the talk on the right-hand side. It even works somewhat decent on mobile. You can check out everything there. Let's go with what's data-oriented programming. So all the programming paradigms, or not all of them, but many programming paradigms have an everything is a sentence, and the idea is to collapse a complex approach to everyday problems into a single and very well understandable sentence. And overall, the goal of a programming paradigm is to manage complexity. Complexity comes in very many different forms, and a paradigm tries to somehow manage them. And they usually do a better job at some kinds of complexities than in others. So structure concurrency was clearly, structure programming was clearly better than GoTo before it. But since then, many programming paradigms are not clearly better across the field. They have strengths and weaknesses. And so when you ask which one to use, then an easy answer is to say it depends. It's also kind of it's not helpful, because just it depends, it doesn't really tell you anything. So I hope to explain to you today not only what data-oriented programming is, but also what does it depend on when to use it. What are good situations and maybe not the best situations to get used to it. Okay, so object-oriented programming says everything is an object, right? That's like the punchline there. And we combine state and behavior in single objects, in classes. It uses encapsulation a lot to guard that state from just everybody changing it. And it uses polymorphism through inheritance. So inheritance is the prime way to apply polymorphism, meaning if you have if you have one operation, but it needs to be done differently depending on which type, so adding to a list is different on a linked list and on an array list, then that goes in Java usually through inheritance, right? You know that add is a method on the list interface, and then linked list and array list have different implementations. So that's what I mean, is that polymorphism works through inheritance mainly in object-oriented programming. And that works great if you want to uphold or define boundaries. So if you are writing a library and you want to uphold a boundary to your clients, or also to your dependencies, you want to uphold boundaries across different versions. You want to make sure that certain security-relevant information isn't handed out. In all those situations, encapsulation and object-oriented programming in general is a great approach. And most of us, I guess, are or see themselves as kind of like object-oriented programmers. We're used to that kind of thinking. And so in most situations, I would say, stick with that, right? Don't go crazy and try all these new paradigms in spaces where you don't feel comfortable with. But one space where I could recommend starting to work with data-oriented programming, and we'll see that later why, is if you have a smaller system that has less need for boundaries, or if it's a system that's very heavily focused on just processing data. And again, as I said, we'll see why that would be the case. This entire talk and even the title is totally ripped off from Brian Getz's article. So Brian Getz is a Java language architect at Oracle. He's a key member of OpenJDK. He's driving a lot of these evolutions of the Java language. And he wrote a long article, and he put forth some guiding principles for data-oriented programming. Model the data, the whole data, but nothing but the data. Data is immutable, validate at the boundary, and make illegal states unrepresentable. And if this would be like a 5-minute lightning talk, I'd now be done, say thank you very much, and go off stage. Clearly, this is not that helpful. So what we're going to do now, as I said earlier, we're going to apply these principles step by step to turn a mediocre object-oriented solution in a pretty good data-oriented programming solution. Okay, so let's go through this example. So why are the lines missing here? They're just supposed to be, and also where's my cursor? It gets worse and worse. Ah, there we go. Okay, there's this line. There's supposed to be another line up here. I'm confused. Doesn't matter. Let's go. So I wrote a GitHub crawler. This is actual real-life code. You can find that on GitHub. It's in a project called Loom Lab, because it also uses virtual threads. So it uses one half as virtual threads, one half as data-oriented programming. You can check it out there. What this crawler does, it connects to a URL, a GitHub URL, and then it tries to identify what kind of page it is. For now, we're going to assume that GitHub only has two kinds of pages, for pull requests and for issues. So it tries to figure out which one it is. Then it tries to find the important or the interesting part of that page, so not the header, not the footer, just the conversation in the middle. Finds outgoing links, so maybe in an issue discussion, somebody linked to another issue, tries to find that, goes with that URL back to step 1 and does it again. If it finds external pages, maybe somebody linked to Wikipedia, it registers that page, but then it stops. And ideally you have some kind of condition where it stops, because otherwise you're going to crawl off GitHub probably. So after like a couple stages it stops. But that's what it's doing. All of that logic is already implemented and doesn't matter to us. It's in this method here, load page tree. It returns an instance of type page. And what we'll be focusing on is what that type looks like and what the rest of the system does with that type and how it operates with that, right? So the whole steps of connecting to GitHub, that's all already done. We're not going to deal with that. We're going to deal with everything that comes after. So let's gather some requirements for this type page. All pages have a URL. Sometimes, you can't connect. Maybe it's a network issue. Maybe you're still in company VPN and it doesn't let you go to other GitHub projects. So there might be an error. If you did resolve a page, it will have some content, and it was a GitHub page, then it will have two other things. It will have an outgoing link, and outgoing links, sorry, plural, to other GitHub pages or external pages too, and it will have an issue number or pull request number. Right? So note that external pages don't have this. If we find Wikipedia, we stop searching there. And then we can make up all kinds of operations that would be possible on this. Right? Since we now scrape GitHub, we're doing this as a service, we're offering all kinds of added features in that. We could display this as an interactive graph. Since we're doing graphs, we might as well compute some graph properties. Maybe we do a categorization by topics, or we do mood analysis, and if we do all of that, we might as well charge people for it. That could all be possible operations on those types. Now, because all of those are complicated and don't fit on slides, I implemented neither of those. So what I implemented instead is just some very simple evaluation of statistics and a way to pretty print those. So those are the operations we have. So now we have some definitions for the state, URL, and maybe content, maybe error, and some operations on that. And the naive object-oriented approach, and even with OOP, that will not be my final solution, but it's, as I said, it's the first throw that you might want to make, is this one. You just create a page which has these fields, URL, content, issue number, whatever. Then you write accessors for those. You might prefer to call them getters and write get URL and get error. I stopped doing that a long time ago. I don't think that's very meaningful to put the get there, but you can think of those as getters. And then at the bottom, you have the two actual operations working on that. That could be an implementation in object-oriented programming. And as I said, this is somewhat naive and has a bunch of issues. And probably the biggest issue is that the page type is implicit. I said earlier, we might find a GitHub page, or we might find an external page, or we might have an error. And that property is somehow encoded in the combination of fields. So if we had a connection error, then we probably have an error message, but we don't have content, and we don't have a pull request number. But that combination, but that type is encoded in those fields somehow, which requires us to make sure that everything was correctly with tests. We should write some documentation that people can understand this. That's very implicit, and everybody using this type has to basically guess. And then at the bottom, we have a problem, which is that we have very disparate operations on the same class. Now, again, evaluating statistics and pretty printing is not that it's not that wild. But if you think we would have operations here that draw this as an interactive graph on a canvas, and also a method here that deals with the payment system because we want to charge people for it, then you have one type that has dependencies on a 2D canvas and on a payment system. And that already should raise some red flags, because that's not great. So if we just put the operations on that type, this type starts knowing all the subsystem it relates to. And that's not great. So we have the issue that there is some state encoded in a weird way, and we have the issue that the operations are all in the same type. So let's work on that. Let's start with model the data, the whole data, and nothing but the data. Specifically the first part. Model the data. What data do we have? We have 4 kinds of pages. That's what I said earlier. We have pull request and issue pages. We have external pages, and we have errors. So we want to use records for each of them. Now, records were finalized in JDK 21, so I assume a lot of you already used it. Who has used records in the past? Great. Okay, for those of you who haven't, we're going to give you a little bit of an example on the next slide. Just overall, the idea behind records is you want to create transparent carriers for immutable data. Note how the message does not say you want to avoid boilerplate. Yes, they can do that, but if you use records to avoid boilerplate, you're going to be pretty unhappy pretty soon. Because there are some limitations that do not make sense under the rubric avoiding boilerplate. They make a lot of sense under the rubric transparent carriers for mutable data. So what happens here is that the compiler understands the internals of a record, couples the API to it, and that's where the boilerplate reduction comes from. This is how you create one. You say record instead of class. You put what's called components here, and then you get a bunch of stuff for free. Like, note that this is the rest of the body of the record. So the body is empty. Nothing else needs to be done. You can do more stuff, but you don't have to. The type is final. It gets private final fields for each component. It gets the accessors, which thankfully also don't use get. You get a constructor, and then you get equals, hash code, and toString that use all components. You can customize a lot of that. You cannot add fields, but every body of all those methods, like the constructor or the accessors, you can modify all of those. If you don't want to use, for example, for external page, equals and hash code arguably should only work on URL, right? Because it's already a unique identifier, so why not use that for equals and hash code? For example, you could do that, and so you can override those bodies to implement it the way you want. Okay, so let's use records for this to model the data. The data was we have an error page, which has a URL and an exception. We have an external page, which has a URL and content. Or we have one of the GitHub pages, which also have URL and content, but they then also have an issue number or a pull request number, depending on what they are. And then they have a set of outgoing links. Right, so now we're very close. Like, this is very unfancy. It's the opposite of fancy. It's just, this is what we want to model, so we just model it literally with records, straight up. Now, the second part of that sentence says the whole data. So what we modeled so far is the individual data points, so to speak, but there is a connection between those. I mentioned earlier that when you connect to GitHub, or when you connect to the URL, you either have a failure, or speaking, you have an error, or you don't. And if you connect it successfully, you either have an external page or a GitHub page. And those things you can express as well. You can use sealed types for that. Now, who uses sealed types in the past? Oh, that's actually surprisingly many. I would say it's like about a third or fourth of the people who used records. And that's understandable because although I guess most of you then would be on 17 or maybe 21, you could use both. Sealed types don't really have a lot of value in 17 yet. They really only come into the maturity with the rest of pattern matching that we're going to go through. So what's a sealed type though? A sealed type is one that communicates to your colleagues and also to the compiler that the number of implementations of a class or an interface is limited. Now I'm going to focus on sealed interfaces in this talk because that makes things easier and simpler for us. So usually an interface can be implemented by everybody who sees it, right? If you have a public interface, everybody in the JVM running on the same JVM can implement it. And mostly that's good. That's what you want, right? If you have a list or collection interface, you want arbitrary implementations as long as they adhere to the contract. But there are situations, and they're not the majority of situations in most systems, but they do exist, where you do not want to do that, where you do not want to have arbitrary implementations because you know your system only really works for like these handful of implementations. If you write a render pipeline and you implement it like triangles and circles, nobody's expecting that if you put in squares, it just works out of the box, right? You would assume that maybe the whole rendering pipeline needs some changes here or there. And if you use sealed types to reduce inheritance or limit inheritance, then you also get exhaustiveness checks. I'm going to put a pin in that and come later back to it. So how does it work? You put the keyword sealed here before the interface, and then you say which types it permits. These types could be other interfaces, or there could be classes, it doesn't matter. And then only those types can implement or extend the interface. Every other type that claims to be an instance of the interface gets errored out of the way by the compiler. It just say, nope, my page does not extend page because you told me only error page and successful page can do that. So with this, we can model relationships between data. So we already have page is either an error or a successful page load. And every page has a URL, so let's put this here for uniform access. And if it's a successful page load, then it must be an external page or a GitHub page. And if it's a GitHub page, it must be either an issue or pull request page. Okay, so all those, 7 types we have now, I put them here in this diagram in classic UML fashion. Blue is interfaces and orange is records. So this is just a regular inheritance interface, or at least that's what it looks like. The interesting bit here is that this entire hierarchy is sealed. I created all interfaces as sealed interfaces. All records are final. And that means if you have, for example, a page, you know it must be one of these types down here. There's just no other choice. There's no other option. Nobody can extend this hierarchy further. And we're going to lean on that heavily later. So this is the much more detailed and improved hierarchy that we're going to use now going forward. Another one was make illegal states unrepresentable. And we already did a lot of that. So in the first proposal that I made, you would have a type that had as a field error and content, for example. But we know those are mutually exclusive. If you had an error while during a page load, you didn't also get content and the other way around. So this combination was legal in the first object-oriented type, the first page type that I showed you, but I would have to check somehow to make sure this combination never exists in my system. Many of these issues are out the window now. There exists no type that both takes an error and a content, so we're good. But there might still be other things going on that we might have to check, and for those you just go into the constructor, or if it's more complicated, maybe into a static factory method and check those there. So let's validate everything else at the boundary, and let's reject illegal states in constructors, or as I said, static factory methods. So for external page here, I'm now writing a constructor. Now this constructor might look kind of weird because where's the parameters? This is what's called a compact constructor. As I said earlier, every record gets a constructor that uses all the components as parameters. That's called the canonical constructor. That always exists. So why do I have to write it out if I want to change it? If I want to change it, I would have to write out the full constructor with all the parameters, and I would have to assign everything to the fields. And I totally can do that if I want to. But also I can use a compact constructor. The idea here is that this is more like an initialization block. So you write external page, and then you write this block. And what this means is all these parameters here, those go in, and I can do stuff with them. I can do checks. I can even do reassignments on them. And once my block ran successfully, then everything is assigned to the fields. It just cuts out the code that I don't need to write because it can happen automatically. But you don't need to write this if you feel more confident with the regular constructor. Now also the compact constructor should always be the first constructor in your record. You cannot have additional fields, so by that logic, this thing would usually be 1 or 2 lines below this list, which I think makes it feasible, to look up 2 lines to see what the components actually are. Okay, good. The last one is data is immutable. Now, unlike the other ones, I would say this is a bit softer. So yes, data immutability plays a big role in data-oriented programming, in function programming, in highly concurrent programming, but there are always local situations where maybe you will need mutability for a while you're putting something else together. But still in most cases, this should be, or rather in all cases, it should be your default, but if you have reason to diverge from it, go for it. Now a record has final fields. That means the fields cannot be reassigned. But if the fields reference something that can be changed, like an array list, then that means somebody can get that array list or this hash set and just clear it or add stuff to it. So that means if you really want to be immutable, you might have to do some extra work. Specifically with collections, that means you need to create immutable versions of those collections, and JDK 10 added these copy-off methods. So here, the GitHub PR page gets a set of links, and I'm just creating a set.copyoff. I'm just creating an immutable copy of that, so that my PR page, when somebody asks my pull request page for the outgoing links, they cannot call clear on it. Or rather, because it's the Java collection framework, they can call clear on it, but they will get an unsupported operation exception. Okay, good. So now we made the page type explicit. We allowed only legal combinations of fields. We made sure that the API is much more self-documenting because you can clearly see a successful page is either this or that. You don't have to add this in prose anywhere. There's much of this code that is entirely untestworthy. Like you do not have to test whether a record constructor assigns the fields correctly. Yes, it does that. Don't worry. So a lot of the tests also went out the window. And so this is overall much better. But we don't have operations. I mean, we had this, gather statistics method earlier. Where did they go? So let's cover them next. The idea, and this is the one where I don't like Brian's approach that much, Brian's guidelines. They said model the data, the whole data, and nothing but the data. And somehow that implicitly tells us, that somehow implies that yes, operations don't go here. I think this could be more explicit. But the idea behind that is that we do not put these methods onto the record unless they only derive some quantities. So if you have a record for a name that has first name and last name as components, then you maybe have methods that give you back first name space last name, or last name comma space first name. Those methods only work on the record components. So they would be described as derived quantities. Those definitely go onto the record. That's fine. Everything more involved should go elsewhere. Now the problem is, for the simplicity of this demonstration led to the fact that these methods actually are only derived quantities. So you could argue these do belong, even with data-oriented programming, they do belong on the record. We're going to act that they don't. We're going to pretend that this is much more complex than it actually is, and we're going to put them elsewhere. And the way we're going to do this, I'm going to explain all the words in there if they don't make sense to you yet. We're going to use pattern matching on sealed types to apply polymorphic operations, and we're going to lean on records transparency to take them apart. So let's start doing that. Type patterns were finalized in Java 16. They do three things at once. They do a type check, a cast, and a declaration. So in this case, you have if the root page is an instance of GitHub page, and let's ignore the GH page there for a second. In the past, after a check whether some instance is of some type, you usually declare a new variable of that type with a new name and then cast the old variable into it. And that's exactly what type patterns do in one go. So it checks whether root page is an instance of GitHub page, declares a new variable, and casts into it. And wherever this check is true, that's where you can use GH page. They can do some nasty stuff with that. If you're interested in that, ask me later. We're going to skip past it for now. The cool thing is Java 21, and that's the big reason why why I would say that Java 21 brought all the basic building blocks of pattern matching together, is only in Java 21 is it a finalized feature to use patterns in switch. So here I'm switching over this page, which is of type page, and then I'm saying in case it's a GitHub pull request page, do something. And it gives me a variable PR of that type. Right? So this means at this point I can make distinctions by type very easily. I say switch over the page, and in case it's this kind of page, do this, or do this. In case it's that type of page, do that. So conceptually, it just runs down the list. That's not quite the implementation, but conceptually, it just runs down the list, finds the first branch that matches, and executes the right-hand side. Exactly like you would expect from a normal switch statement as well. This is just some setup code for the statistician. The interesting part is here. So the statistician has these number of fields. Oh, wait, let's go back though. This method here evaluates the statistics on given a root page, it evaluates the statistics. So you can see that the page comes into the statistician. Whereas if you put the method onto the page, then it goes the other way around, like the control flow goes the other way. So here, the control flow comes through this evaluate method, and for each individual page, this method gets called. So given some page, we don't know which one though, evaluate that. Okay, and the way we do this now is we say, okay, in case it's an issue page, then increase the number of issues. We just want to count how many issues we have, how many pull requests we have. That's what the statistician does. These are all fields, and so depending on the type that we have, we increase the correct field there. Okay, so far so good. We can do the same thing for statistics, for pretty printing. Again, some setup code, more for completeness sake than anything else here. And here we get a page and we return a string. We're using switch as an expression, so we put return here. The entire switch evaluates to a string in the end, and we're saying in case it's a GitHub issue page, execute this branch. Now, if the slides would not be that narrow, you could put this on one line, which is very readable. And what it tells you is, well, if it's an issue page, then apparently the result is the cat and issue and the hash, and then the issue number. Now note that I'm really relying on this typecasting here. I cannot call issue number on page. That method doesn't exist. I need it to be of type issue so that I can call this number, right? So this method, right? So I'm really depending on these typecasts here that happen. So for each type, I write a branch that processes it according to what I need. Yes?
Yes, I'm noticing this is more functional style rather than style. Okay.
So Mario just said that this is functional, which pretend he didn't say that for another, 20 minutes. Good. And so, but actually, that's a good slide to stop me for a second, though, because if you only take away like one slide from this talk, it's this one. What this does is it takes in a type, it has to execute an operation, that's polymorphism, And it does polymorphism in a weird different way where it just checks the types manually and then does the correct operation. And from now on, we're going to spend a lot of time making this easier, explaining why it's safe, doing some follow-up conversation. But this is basically the takeaway. This is what you can do. Now we're going to go into why that's not a terrible idea, even though it might look like one, and how functional it really is. Okay, so let's take one step further. Let's use record patterns. So records are transparent. That's what I mentioned earlier. The compiler understands the internals. And one way I can use that is if in a switch like this, if I do not need the external page as a page instance, if I just need the content, I can just immediately destructure it. So what this does is not really magic. It's just a shortcut for, in case it's an external page, create variables URL and content, and then call on the call on the record .url and .content and assign it. I do not have to use var here. I can use URL and string, which arguably would make this a little more readable or safe, but it's fine, right? Like it works just fine, and you can use var here as well. It's the same trade-off as var has everywhere. So we can use it here, for example. So for the error page, that makes a little bit more sense. So for the error page, I'm saying I take it apart into URL and the exception, and then I only need the URL get host here. And for the issue page, I take it apart into all its 4 constituent components, and I only need the one of them. Now this is more cumbersome than the solution before, right? I now replaced calling issue number with splitting it into like 4 components, 3 of which I don't need. And this is common. Not having to use all of those components is common, so that's why we get unnamed patterns. Unnamed patterns, that's the first feature I'm showing you that is not final in 21. It's in preview in 21, it's final in 22. Quick word on preview features. A preview feature is not an alpha or beta feature. It's not a green banana that you buy in the store. It works. It does everything you want it to do. It's as safe and as performant as everything else that you expect from Java, but it's not yet as stable as what you expect from Java. It might change in the future. And so what you do not want to do is you do not want to use a preview feature in your production code base, heap 2 years worth of code on it with like 10 different developers, and then have to rewrite all of that because there was a change to the syntax. So preview features are there and they're good, but they might still change. Now in this specific case, you know that they don't. So if you really have to use this feature, you can. Again, I'm not here to recommend you to do that because you have to add the enable preview flag, and from that moment on, all previews are fair game, and all your colleagues can use previews that might definitely still, or not definitely, but might change in the future. But what I'm saying is if you have an internal code base, maybe, right? If you're tracking vacation days or something, like small things where you're willing to rewrite a bunch of code if it becomes necessary, those are great situations to start using preview features, experiment with them, understand how they're working, and if you found any issues, give feedback on the OpenJDK mailing list. That's why we have them. So, stuff that code that isn't public facing, demo projects, just explorations, right? Maybe you write a little prototype on something unrelated. Why not throw in a little bit of preview features from Java, learn about them at the same time. Okay, so with those, what I can do is I can replace all the variables I don't need with an underscore. So GitHub issue page, I just put underscores here because I don't need all of those, I just need the issue number. And I do the same thing for the error page. If you put all this together, you get this. And now again, unfortunately, the narrow slides make it look a little bit less elegant than it actually is. What I find really great about this way to write this is that the left-hand side of this arrow, so this arrow, and so the left-hand side, which is the row above it in this case, tells you what I'm interested in. I'm interested in the issue number of the issue page. And then the right-hand side does something with it. And often we're just reading code, we're scanning code, we're looking for the place where the bug might happen or we can insert the new feature. And often we're in a high level, I just need to like roughly figure out what this code is doing mode. And in that mode, that's excellent. You can just scan down the left-hand side of all these case labels and see this one pulls the issue number, this one pulls the pull request number. I'm not looking for that, so let me scan on. So I think it's a considerable improvement. Okay, now I need some audience participation. Isn't switching over types bad? We've all kind of learned that, or if we didn't learn it like in high school or in university or in programming course, we might have learned it the hard way, that it's a really bad idea to switch over types. Who thinks that like instance of checks everywhere in the code base are a code smell? I mean, it's a trap, you know that, right? But yes, thank you. I mean, actually, the instance of check is still a code smell. So why is that a code smell though? What's the bad thing about it? Yes?
Because if you're doing object-oriented, you've probably got some operation there that should be on the object itself.
Right, so the argument is if you're doing object-oriented programming, the operation should probably be on the object.
And it would be the different thing that you do in the different cases would be on the different subclasses.
Right, and then they would go into the different operations, go into different subclasses. I'm just repeating you for the remote audience. That makes sense, that's correct. But why though? Why does object-oriented programming say you should do it this way? Yes?
If I have to add another type,
Yeah.
to touch all these places.
Right. So you add another type. If you have an interface method and you add another type, well, the compiler forces you to implement the operation for that type. But if you have like a series of instance objects, it's all good. The compiler is happy. And the terrible thing about that is that you have to somehow find all of those places. And you basically have to resort to regex search to find them because there's no good way to find those places. So when new types are added, something happens. Yeah, like it's not clear what exactly happens. If you're lucky, you find it in code. What did Venkat say yesterday? If you're lucky, it fails on your machine, and if you're unlucky, it fails in production. If you're really unlucky, it fails in production, you cannot reproduce it, something like that, right? All of these cases are on the table here. But this is different. Let's say the product owner figured out that GitHub has commit pages too, and now we need to implement those. Let's do that. Let's write GitHub commit page implements GitHub page, and let's follow the compile errors. We put the record here, and we say implements GitHub page. But remember, GitHub page is sealed, so the compiler yells at us. The super type is sealed, you cannot do this. Okay, so we keep the code like this, we go to the super type. We add the new type here, we say now we allow the GitHub commit page. And now, all of these break, because they are no longer exhaustive. I used that word earlier, but I didn't really explain what that means. If you write a switch that is an expression, meaning it has a return before it, or like a variable assignment or something else, or if it's a switch that goes over a complex type like this, then it needs to be exhaustive. It needs to cover all possible subtypes. And because page is sealed, the compiler knows, remember the diagram that we had earlier, that these 4 types actually do cover all possible subtypes. If I deal with all of those 4 types, I'm done. I exhausted all options. That's why the compiler was happier before. I didn't tell you that though. Now, this switch is no longer exhaustive, and you get a compiler error. So the compiler will point you to all the places where this new type needs to lead to a change in code. And that's why it's safe. It's compiler support for adding these new types. Now, as I said, like it needs to cover all cases. The problem is you can also just have a default branch. We did the enumerate all subtypes versions, but you can also have a default branch, right? A default branch also means like all cases are covered. But then if you add a new type, still all cases are covered. So default branches are not your friend here. We need to avoid those. So, right. So we add the type here. That's what I didn't show you yet. So now the compiler error is gone. Everything is good. Let's go back to avoiding the default branch in a second. Because to keep this maintainable, you want to always switch over, well, in this data-oriented programming paradigm. There are other situations where you might want to switch over other types. But if you want to do this data-oriented programming paradigm where you implement your operations outside of the type, then you want to switch over sealed types. You want to enumerate all possible subtypes, even if some of those you don't really need to treat, and you want to avoid the default branch so you get that compile error. That's very important. Second most important slide of the presentation. Now, avoiding the default branch. Let's say we have this example here where I get the cat and the octopus as emojis for the GitHub pages, but all the other pages don't get an emoji. They get just the non-available, the NA. Right, so this looks good-ish, but if I add the GitHub commit page, this still compiles. It's still exhaustive. Adding the default branch was a mistake. On Java 21, what you have to do is this. You add 2 branches for each extra type. You cannot combine these branches because with these variables here with the error here, sorry, like I was like weird. Okay, with the error here, you can use error on the other side. If you would combine these branches, which was implicitly an or, case it's this or it's that, then you couldn't use either of the 2 variables because you don't know which one of is actually which type it actually is. So you cannot combine these. If you put explicit variable names there, you have to duplicate them. And this is where, once again, unnamed patterns come in. This is the real strength of these unnamed patterns. It's not that you can do it while destructuring. I didn't even tell you that, but you can also use that in lambdas, for example. If you have a by function and you don't need the second parameter, you can use the underscore there. That's all nice. But this is really important because this gives you a good way to create defaulty behavior without having to use an outright default branch. So this way you can combine the two branches because whether it's an error page or an external page, you're not referencing a variable on the right-hand side anyway. So it's all good. You cannot reference the underscore. So it's all good. This way you get default behavior without a default branch. Okay, so where were we? We separate the operations from the data. We made adding new operations easy. You just add a new switch, type down your functionality, and you're done. And adding a new type is a little bit more work. When you add a new type, you have to go across all operations and add them everywhere. And but the compiler leads you to those places. Yes?
Yeah, just before you move on, can you briefly say, if I was an object-oriented, what's the word, maniac, not,
Yeah.
I would say it's not only about detecting that you need to put the changes in these 5 different places across your code base, it's also about cohesion. You're going to make the changes all in the one class where you need to make those 5 different operations. It's going to be your new stuff, right?
Yeah.
Just sort of briefly say, why is it good in certain, or at least okay in certain contexts?
Yeah, so the question is, the object-oriented programming was not just there to give me compile errors, it also keeps things that belong together in one place, right? And this does not do that, right? So how is that a good thing? So I got a two-part answer. The one part is basically what I just described here. So in this case, we had doing it now. If I add a new data type, it's work because I have to go across all operations. If I add a new operation, that's simple. Note how this is the inverse of how it works in object-oriented programming. If I add a new method to an interface, I have to go across all types and implement it everywhere. But if I add a new type, I just sit down and write down the type. So it's the flip side of the same coin, right? That's what I meant. That's like a very, very tiny example of what I meant earlier, that different paradigms handle different kinds of complexity differently well. It's not a huge difference, right? But you can tell how one thing is slightly different than the other. Now, object-oriented programming teaches you to think about the object and the instance and the class at first. And so it might seem weird that I have to go across all the operations because the cohesion, and for the object-oriented maniac that you just mentioned, the cohesion is the type. But if the cohesion is the operation, then this makes more sense because now I can see the operation in one place. And note how this is like the visitor pattern. We had a good talk earlier about patterns. Thankfully, the visitor pattern was not in there. This is what the visitor pattern provides you with. It provides you with a way to put operations elsewhere that are not part of the API, but to still get compiler support that when you add an operation and you add a type, in every situation you get compile errors until you made everything work with everything else. And that's something we're going to look at in a minute. Okay, so we're good on time. We just did the part that we absolutely had to do, and we can now go a little bit of a review phase. But this is also a great time to ask some questions if you have any more. Otherwise, I'll dive into that. We're going to come to the functional part. Don't worry. Probably soon, actually. Okay, I don't see questions. I'm just going to go on. Right, so let's talk about dynamic dispatch. Dynamic dispatch is the technical instrument which makes sure that you invoke the right method on the right type. And we get that as a language feature with inheritance. At runtime, basically what happens is that the runtime has to figure out when you call list.add, what actual instance you called it on has to do conceptually like a little switch over the subtype and like figure out which type exactly to call. That's not actually what happens, but you can imagine it that way. So we get inheritance as a way to implement this dynamic dispatch. But that makes the method part of our API. That's why list.add is on the list interface. And that's great in many, many, many cases. But there are cases where it's not great. There are cases where we do not want to overload a type with all of these operations. And that's why we have the visitor pattern, for this exact reason. Now, the method is no longer type of the API, but this visitation aspect is part of the API. And it's also a very cumbersome and indirect pattern. Like, it's not fun to understand. Like, specifically, I still remember when I was a young programmer, my second large code base that I worked on used the visitor pattern extensively. For good reason. It was the correct solution for the problem that they were solving. But man, was it confusing to me. It's like, you're always like, okay, so what's happening here? And then you say, like, you call, visit this. And you're like, oh man, what's happening now? So it's like, it's not trivial to understand and to follow along. And now, We got a third way to have dynamic dispatch, which is with the pattern matching. It leaves the original type almost unchanged, except that it makes it sealed, which is not a trivial limitation, but it's much less impact on its overall, visibility and structure than giving the visitor pattern. And from then on, it's straightforward. Switch over the type, implement your operation, and off you go. So, a word on patterns and language. Again, we had like a great talk about patterns earlier. I'm not sure I totally buy into this, but there are people who make a convincing argument that patterns are only a thing where the language lacks something. You only think about a pattern if it's a thing you need to actually do, right? So still remember the old days. At some point, I got my hands on the Gang of Four book. I learned the patterns. I tried to apply them where they were meaningful, and I felt good. Like I had a problem, I sat down, I solved it with a strategy pattern, and would go home and be like, "Good job, Nicolai. You can go home at like 2 p.m. Like you did a good job today." Now, every time you pass a lambda, you have some of these behavior patterns in play. It's not always a strategy pattern, I was told. I don't care about the details anymore. The point is, every time you pass a lambda, you're using some behavioral pattern. I'm pretty sure nobody thinks about it that way. You're just using a language feature. You're not doing a pattern. You're just, creating a lambda and passing it to the optional stream API. So once the language makes something sufficiently easy, it's just the language and no longer a pattern. And that's what this does for the visitor pattern. It just, poof, goes away, and we just have another way to do the same thing, simpler and easier. So where can you use this? In pretty many places. Ad hoc data structures, I'm going to show you a little bit about that. Complex return types, or even in more complex domains. I mean, the page example was not that complex, but that's what I mean by that. So one thing is ad hoc data structures. You just want to have some type quickly. You need it locally a little bit. You can use records for that. If you have 2 or more of them, you might do a switch over that. This is a record that comes from the GitHub crawler. I already have the page. I parsed everything, but I'm still putting together the links. So I need this to be a mutable set of links, of URIs, so I can add more URIs here. So that's what I'm doing here. Like I went above and beyond by having an additional constructor that takes like an empty, that does not get a set as input. I make a copy of the set here to make sure it's actually mutable. I didn't have to do this. This is an internal class. I might have just kept it to a one-liner. So if you're in a situation where you need to combine data just locally, just a little bit, don't wonder why Java doesn't have tuples. Remember, records make it super easy to put data together. They are tuples. They are nominal tuples. Tuples based on a name. Whenever you need 2, 3, 5, 10 things put together, well, if it's 10, evaluate whether you actually need 10. But up to that number, create a record as exactly as you need it, use it a little bit, and throw it away when you don't need it anymore. You can also do something more complex. These are often return types where when an operation has like different outcomes, and you want to present the different outcomes to the user. Let's start at the bottom here. You have a find user method that takes a username and gives you back something that's called a match. And a match is a sealed interface, and I didn't put the permits clause here, that has 3 implementations, none, exact, and fuzzies, which is there was no match, there was an exact match, and there were a bunch of almost matches. This is how you use it. Find user John Doe, you switch over it, and then you say case I didn't find any, case I found exactly one, case I found a bunch of those. I would argue that this code is supremely readable. Like as a reader of this code, I immediately know what's going on. I don't even need to read the Java doc of find user. I don't need to figure out whether find user gives me back a type, whether I have to check the state of the type to know which one of these variants it is. No. Match, so the match interface has 0 usable methods. The only thing I can do with it is switch over it to figure out which exact case I'm in. This is how many languages implement optional. They often have a maybe type that has like a some and a none implementation. I'm not sure whether Java would implement optional this way nowadays, but it could. But no, we're not going to revamp optional though, so it's going to stay as it is. Or you can use it throughout your domain, right? If you're long-living objects like the ones I just showed you, complex again, in quotes probably. But yeah, you can do that. I'm going to skip past the algebraic data types, even though there is something interesting for functional programmers. Let's talk about functional programming though. I talked about immutable data structures. I talked about functions, could I say functions, that operate on them. Isn't this just functional programming? And the answer is, yeah, kind of. Like you caught me, Mario. It's basically that. He just asked because he wrote a good book about functional programming in Java 8. And that's exactly what this kind of stuff is exactly what's in there, right? Functions, immutable data. I think it's just a difference of emphasis. So if you have object-oriented programming here and functional programming here, then data-oriented programming is like a neighbor over here somewhere. Sometimes you make trade-offs. Sometimes you are in a situation where you don't know what exactly where I'm going, and in those situations, functional programming, and I'm saying this theoretically, I did not do functional programming outside of Java very much. Functional programming probably leans more towards prioritizing creating reusable and composable functions, whereas data-oriented programming leans more towards making sure that you model the data as the data, and if the function needs to look a little bit awkward, then that's okay. So that would be my definition of the difference here. Wait until Mario took the picture. There we go. So I'm not telling you that all object-oriented programming is dead. Again, that's not what this is about. If you're like, you can clearly do complex problems entirely functional, and if you want to do that, that's great. If you want to do that in Java, you got just more tools. That's all great. But if you are an object-oriented programmer, then that should still be, or would still be, your default approach, right? Turning a large problem into many smaller problems, focusing on those in isolation, all that good stuff still works. But once the problem becomes sufficiently small that you feel like all this encapsulation, all this inheritance maybe is not needed here anymore in this local area, or if it's very data-centric, in those situations you can try using data-oriented programming locally. That could be a package in a larger program, but there could also be an entire microservice if you have like a small service. And I would recommend, if you want to try this out, to try it out in one of those smaller, limited environments, experiment with it, understand it, and then take it from there if you like it, if you feel like it solves your problems well. The GitHub crawler was the first project where I used it. That was, I want to say, like a year and a half ago. I'm not sure exactly when. And since then, I've used it 2 or 3 times in other projects that came up. These other projects are also like small-ish projects that are like either demos or stuff that like very small, that lives in production somewhere. But they came up out of their own. They did not come up because I wanted to use them. They came up because it turns out once you have the solution in your belt, it kind of makes sense in a lot of situations. And so I can really invite you to look into that. So as a summary, use Java strong typing to model data as data. You want to use classes, specifically records, to model the data as closely as possible. You want to use sealed classes or sealed interfaces to differentiate alternatives. It's either this or that. Use sealed types for that. And then you want to create every meaningful operation that your system does as a function elsewhere on some subsystem, on the payment subsystem, or on the canvas drawing subsystem, on the graph analysis subsystem, and as input, they take instances of these data classes of these records, and then you use exhaustive switches without a default branch, and then you use pattern matching to destructure the data locally and use what you want. And if you want to read more about that, I'm going to post about the links later on social media, and I'm not sure whether the organizers collect them. Conference organizers collect them. They're also on slides.nipafx.dev. These are all links, but if you take a photo and search for these terms, you will find the YouTube videos, you will find the sources somewhere online. And yeah, thank you very much for your attention, and wish you a great conference. So we're out of time, but I think there's a break now, if I'm not mistaken. So I'm just going to stay here to let you ask questions, and otherwise, I'm easy to recognize. I'll be outside for the rest of the day.